This is SpaceTime Series 27, Episode 42, for broadcast on the 5th of April 2024. Coming up on SpaceTime, claims that water persisted on Mars' Gale Crater for longer than previously thought, the Sun's spectacular double solar flare, and persistent reports that the Pentagon really is testing a successor to the SR-71 Blackbird. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have found signs that water was abundant in Mars' Gale Crater long after the red planet was thought to have become dry and inhospitable. The findings, reported in the journal Geology, have implications for science's understanding of the changing climate on Mars, as well as where scientists should be looking for signs of habitability. Billions of years ago, Mars was home to abundant water, and its Gale Crater contained a large lake. Gradually, however, the climate changed, turning the once warm, wet world into a dusty, freeze-dried desert. Using data and images from NASA's Mars Curiosity rover, the authors found clues of deformed layers within a desert sandstone that they argue could have only been formed by water. Now, while they agree that water was present early on, they're uncertain as to whether it existed as a pressurized liquid, an ice, or a salty brine. The study's lead author Stephen Banham from Imperial College London says the sandstone revealed that the water was probably abundant more recently and for longer than previously thought. He says it might have been a pressurized liquid forced into and deforming the sediment, frozen with a repeated freezing and thawing process causing deformation, or briny and subjected to large temperature swings. What is clear is that behind each of these potential ways to deform the sandstone, water was the common link. Scientists accept that most water on the red planet was lost by the middle of the Hesperian period, which lasted from 3.7 to 3 billion years ago. These new findings suggest that water was in fact still abundant underground near the surface of Mars towards the latter Hesperian. To better understand the planet's past climate and suitability for life, researchers are using the Curiosity rover to look for clues in the Mars rock record. The six-wheeled car-sized mobile laboratory has been exploring the 154-kilometre-wide Gale Crater basin just south of the equator, as well as the northern flank of its central mountain called Mount Sharp, since 2012. The 5.5-kilometre-high Mount Sharp was built up in layers, first by incoming lake and river sediments, and later by desert sediments and winds during Mars's supposed period of drying. Using Curiosity's main scientific instrument, Mastcam, researchers collected images of Mount Sharp's sedimentary layers to find the fingerprints of how the rocks were formed. They were looking at rocks that were deposited in what is now a sandy desert and found structures within that indicated water. Banham says that when sediments are moved by flowing water in rivers or by the wind blowing, they leave characteristic structures which can act like fingerprints of the ancient processes that formed them. As Curiosity has continued to ascend Mount Sharp, it's encountered increasingly younger rocks deposited in progressively drier environments. It eventually reached a sandstone deposit draped over the mountainside known as the Stimson Formation, the preserved relic of a desert containing large sand dunes. The images it collected revealed that the formation was deposited after Mount Sharp had formed during Mars's period of supposed drying. They also revealed that part of the formation contained features that had clearly been influenced by water. Usually, the wind deposit sediments are very regular in predictable ways. But surprisingly, these wind-deposited layers were contorted into strange shapes, which suggested that the sand had been deformed shortly after it was laid down. It's these structures which point to the presence of water just below the surface. Generally speaking, the layers of sediment in the crater reveal a shift from a wet environment to a drier one over time, reflecting the transition of the red planet from a humid and habitable environment to an inhospitable desert world. But these water-formed structures in the desert sandstone show that water did persist on the red planet much later than previously thought. The researchers' discovery has implications for future space exploration missions, especially those searching for life beyond Earth. On Mars, the Stimson Formation and similar desert sandstones were previously considered less promising targets when hunting for biosignatures, evidence of past primordial life. Needless to say, finding these water-formed structures changes that notion. This is SpaceTime. Still to come, the Sun erupts with a spectacular double solar flare. And could the aurora be real after all? Persistent reports that the Pentagon is testing a successor to the SR-71 Blackbird. All that and more still to come on SpaceTime. The Sun has become increasingly active over the past week with an almost continuous display of solar flare activity, including a spectacular double solar flare event described as the most powerful eruption since 2017. The growing spate of solar flares spewing into space suggests the Sun is getting very close to solar maxima, the climax of its 11-year solar cycle. After a month of relatively low-level activity, the Sun's now produced a powerful X1.1 class solar flare, followed by almost a dozen smaller M-class solar flares and a bright coronal mass ejection, triggering spectacular auroral activity at higher latitudes here on Earth. Solar flares are an eruption of electromagnetic radiation in the Sun's atmosphere caused by the snapping of twisted magnetic field lines above sunspots. Sunspots are cooler, darker regions of the Sun's surface that form when magnetic field lines rise from deep below the Sun's visible surface. The spectacular X1.1 solar flare resulted from 2 sunspots and was directly targeted towards the Earth. Solar flares are classified by severity, with B class being the weakest, followed by C, M, and X being the strongest and most powerful. The jump from one letter to the next constitutes a tenfold increase in energy output, much like the Richter scale for earthquakes and the enhanced Fujita scale for tornadoes. When a big solar flare occurs, it's often followed by coronal mass ejection, a massive release of plasma and magnetic field from the Sun's outer atmosphere. Now, if one of these solar mass ejections happens to be pointing towards the Earth, they'll trigger powerful geomagnetic storms as the charged particles from the Sun slam into Earth's magnetic field, causing the whole magnetosphere to literally wobble like jello. The ionized particles then travel along Earth's magnetic field lines towards the north and south poles, in the process triggering the northern and southern lights, the aurora borealis and aurora australis. But they can also take out satellites, short-circuiting equipment. They can cause communications and navigation system blackouts, increase radiation doses to astronauts in space, and affect power grids and communication systems on the ground. For this event, for the first time, the European Space Agency's unlikely space weather duo, Smos and Swarm, were able to track the severe solar storm as it warped Earth's magnetic field. For Swarm scientists monitoring the Earth's magnetic field, it was the perfect opportunity to put the 3 satellite constellations' new near-Earth real-time data to good use. Each Swarm satellite carries a magnetometer to measure the strength of Earth's magnetic field. The magnetic field around the Earth is constantly changing, and it responds especially strongly to space weather events. And the coronal mass ejection triggered by the double solar flare event arrived much sooner than expected, causing a powerful geomagnetic storm reaching severe levels. As the data quickly became available, Swarm Alpha was the first of the low Earth orbiting satellites to measure changes in Earth's magnetic field, and Swarm Bravo soon provided another perspective, showing large changes to Earth's magnetic field reaching lower latitudes during its peak. While the solar storm itself was relatively short-lived, the disturbance to Earth's magnetic field was incredibly strong, and the impacts are still being analysed. Now, according to the European Space Agency Space Weather Office, the active region of the Sun responsible has been releasing further M-class solar flares, though not quite as strong. And there's still a 40% chance of further X-class flares in coming days before this active region of the Sun rotates to the Sun's opposite side away from Earth. Now, somewhat surprisingly, ESA's Soil Moisture and Ocean Salinity satellite Smos was among the first in line to capture the solar radio burst associated with the flare. See, the main instrument on Smos is an interferometer radiometer, which normally detects L-band radio waves emitted from Earth. This allows scientists to measure geophysical parameters like soil moisture, sea surface salinity, and sea ice thickness. This report from ESA TV.
On November the 2nd, 2009, Smos was launched from the Plesetsk Cosmodrome on top of a rocket launcher. Smos is one of ESA's Earth Explorer missions that address key scientific challenges and demonstrate new technology in space. Carrying a novel instrument to return information on soil moisture and ocean salinity, both key components of the Earth's water cycle, Smos is advancing our knowledge of how water is cycled between the Earth's surface and the atmosphere. Understanding these exchange processes is crucial for understanding climate change, for improving weather prediction, and, for example, helping to optimize water consumption when growing crops.
Smos measures directly the surface soil moisture. So this is really the kind of rain gauge of the atmosphere. So we collect the rain and we store it. Measuring surface soil moisture gives us a hint on the rainfall, so we can partition the rainfall. But also looking at its evolution, we can link it to different other things. One of them is, of course, dryness or wetness of the soil, so floods or droughts. But also the fact that the impact of other events, such as El Niño, La Niña, and its impact on the rainfall distribution, hence the wetness. So it is used to infer droughts or monitor the droughts, but also, of course, for food security in many regions, to anticipate crop yield, especially in areas which are limited by rainfall.
This research satellite was originally planned to be in orbit for 5 years. But thanks to Europe's technological excellence, it has already doubled its life in orbit, providing time series data for a variety of applications. For instance, Smos data is used for ESA's climate change initiative, through which data are compiled to understand how climate variables are changing over time. Its data are also combined with data from other satellites, such as Cryosat, to map the thickness of sea ice, a crucial climate variable.
With Smos, we have the possibility to measure the sea ice thickness. In particular, the thickness of thin ice we can measure with Smos. We have also the companion, the ESA Earth Explorer Cryosat. This was specifically designed to measure the sea ice thickness, and Cryosat is great to measure the thickness of thick ice from the freeboard. But with Smos, we can accurately measure the thin ice.
Smos data are also used to map the freezing and thawing of soil. This is important because frozen soil, and in particular permafrost, acts as a carbon sink. When permafrost thaws, carbon is released back into the atmosphere, amplifying the greenhouse effect. By comparing data over several years, Smos helps us to better understand variables affected by and affecting climate change. Over the years, Smos has proven to be a versatile satellite, going way beyond its original scientific goals. Today, Smos data are even used operationally for weather prediction by organisations such as the European Centre for Medium-Range Weather Forecasts.
Smos is very important for weather prediction because weather is related to forecast of the atmospheric variables, but it's also related to land surface forecast and ocean forecast, river forecast. And for this, for weather prediction, our strategy is to develop an Earth system approach where we have a consistent forecast for the different components of the Earth system. And in this context, variables which are at the interface between land surface and atmosphere, or ocean and atmosphere, are very important to ensure the consistency across the different Earth system components. And Smos is exactly that. It is providing information at the interface between the different Earth system components.
Smos has given the scientific community an unprecedented wealth of data. And while it has long surpassed its intended lifespan, Smos remains hard at work while new missions are being studied and prepared to ensure continuous datasets with even higher resolutions and improved technology.
Now, due to its position in orbit, however, Smos's antenna also has the sun in its field of view, and solar flares also release radio waves. Now, for Earth observation, these signals are removed as noise. But space weather scientists had other ideas. With almost 24 hours of near real-time monitoring of the Sun, Smos can detect the effects of solar flares on global navigation satellite systems, as well as flight radar and L-band communications. Having this near real-time information is incredibly useful. For example, following an especially strong solar flare in December last year, a number of satellites lost their GPS contact with ground stations in South America. Smos was able to narrow down the cause, linking it to the solar event. This is SpaceTime. Still to come, is Aurora real after all? Persistent reports that the Pentagon is testing a successor to the SR-71 Blackbird. And our nearest neighbouring star system, Alpha Centauri, the iconic constellation Southern Cross, and the annual Lyra's meteor shower are among the highlights of the April night skies on Skywatch. There are persistent reports coming out of Washington that the Pentagon has developed and is now testing a successor to the famous A-12 SR-71 Blackbird, the world's fastest jet. The unconfirmed reports suggest Lockheed Martin's Skunk Works in California are working on a new unmanned hypersonic aircraft, a so-called SR-72 son of Blackbird, which will be ready to take to the skies next year. The secret hypersonic aircraft is said to be capable of Mach 6. That's over 6,400 kilometers per hour, and that would make it the fastest plane ever developed. Its primary functions will likely be intelligence, surveillance, and reconnaissance gathering activities, similar to those undertaken by its predecessor, the Blackbird. The aircraft's combat systems are said to be able to launch hypersonic weapons faster than any other weapons-carrying platform, meaning they can instantly achieve hypersonic speeds. Like its SR-71 predecessor, the SR-72, whether it's called Dark Star, Aurora or whatever, will be about 30 metres long, incredibly stealthy in shape, and fly at altitudes of around 90,000 feet or more. Power will come from fully reusable turbine-based combined cycle hypersonic engines, which combine turbofan engines used for takeoff and landing with a supersonic combustion ramjet or scramjet capable of achieving and sustaining speeds above Mach 5. The SR-71 was originally developed as the Black Project from Lockheed Martin's A-12 reconnaissance aircraft during the 1960s by the company's highly secretive Skunk Works. The original A-12 could reach altitudes of over 80,000 feet or 24 kilometres and at a top speed of over Mach 3.1. The SR-71 derivative could reach over 90,000 feet and a speed of Mach 3.2. It was slightly longer and heavier than the A-12, allowing it to hold more fuel as well as a two-seat cockpit. Now, as far as we can tell, 12 A-12s were built for the CIA, followed by 2 M21 drone carriers, 3 YF-12 high-altitude interceptor prototypes for the US Air Force, and then 32 SR-71 strategic reconnaissance aircraft. The spy planes kept flying until the late 1990s, with the last being used for scientific research by NASA. They currently hold every aviation speed and altitude record for an air-breathing jet aircraft. This is SpaceTime. And time now to check out the night skies of April on Skywatch. April is the 4th month of the year in the Gregorian calendar and the 5th in the early Julian calendar. The Romans gave this month the Latin name Aprilis. Although the name's origins aren't certain, traditional entomology suggests it's from the verb aperire, to open, as in it being the season when the trees and flowers begin to open as the northern hemisphere moves into spring. April is also Prevention of Cruelty to Animals Month, and so it's a good time to consider adopting a shelter pet or donating to an animal welfare charity. High in the southern sky during April, you'll find the Southern Cross and its 2 pointer stars, Alpha and Beta Centauri. The more distant of the 2 pointer stars from the Southern Cross is Alpha Centauri, which also happens to be the nearest star system to our own. Located some 4.3 light-years away, Alpha Centauri actually consists of 3 stars. There's Alpha Centauri A and B, which orbit each other, and Proxima Centauri, which orbits the pair. and at 4.25 light-years distant, is currently the nearest star to the Earth other than the Sun. A light-year is about 10 trillion kilometres. The distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Like the Sun, Alpha Centauri A is a spectral type G yellow dwarf star. It's slightly bigger, having about a tenth more mass than the Sun, and has about 50% more luminosity. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in, spectral type K orange stars, and the coolest and least massive stars of all are spectral type M red dwarf stars. Each spectral classification is further subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and then a Roman numeral to represent luminosity. So, our Sun is a spectral type G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars called brown dwarfs. These are sometimes born as spectral type M red dwarf stars, but become brown dwarfs after losing some of their mass. Brown dwarfs fit into a category between the largest planets, which are about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are around 75 to 80 times the mass of Jupiter, or about 0.08 solar masses. Orbiting in a binary system with Alpha Centauri A is Alpha Centauri B, a spectral type K orange dwarf star, a little smaller and cooler than the Sun, with about 0.9 times the Sun's mass and about half its luminosity. Alpha Centauri A and B orbit each other around a common centre of gravity every 79.91 Earth years. The distance between the two stars varies between roughly that of Pluto and the Sun and that of Saturn and the Sun. The third star in the system, Proxima Centauri, sometimes called Alpha Centauri C, is a spectral type M red dwarf star, with roughly a seventh the diameter and about an eighth the mass of the Sun. It takes around 550,000 Earth years to orbit Alpha Centauri A and B. The nearer of the two pointer stars to the Southern Cross is Beta Centauri, also a triple star system, but this one located a far more distant 390 light-years away. All three are massive young blue stars, far larger and more luminous than the Sun. Two of the stars, named Beta Centauri AA and Beta Centauri AB, orbit each other, while the third star, Beta Centauri B, orbits the primary pair every 1500 Earth years. Beta Centauri AA and AB are known as a spectroscopic binary, orbiting each other every 357 Earth days. Spectroscopic binaries are double-star systems orbiting each other so closely and at such an angle that they can only be visually separated, from our point of view here on Earth at least, by their spectroscopic signatures. Both these stars are now reaching the end of their time on the main sequence, and will soon run out of the core hydrogen they use for fusion, the process which makes stars like the Sun shine. The two pointer stars, Alpha and Beta Centauri, are named after Chiron, the Centaur, a mythological Greek being half man, half horse. Chiron taught many of the Greek gods and heroes, but was placed among the stars after accidentally being shot with a poison arrow by Hercules. Next to the pointer stars is the spectacular Southern Cross, or Crux, the smallest but one of the best known of the 88 constellations in the sky. The Southern Cross is considered an important constellation for navigation and is featured on the flags of several nations, including Australia, Brazil, New Zealand, Papua New Guinea and Samoa. In April, the Southern Cross lies on its side in the early evening, but becomes more and more upright as the night progresses. The bottom and brightest star in the Southern Cross is Alpha Crucis, or A Crux, which is actually a multiple star system located 321 light-years away. It consists of three stars, A1 Crucis, which is a spectroscopic binary, and A2 Crucis. A2 Crucis and the primary star in A1 Crucis are both spectral type B blue stars, with surface temperatures of 26,000 and 28,000 Kelvin respectively. The two components orbit each other every 1,500 Earth years at an average distance of around 430 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, roughly 150 million kilometres or 8.3 light minutes. The spectroscopic binary A1 Cruus is thought to comprise two stars, with about 10 and 14 times the mass of the Sun respectively. The pair orbit each other every 76 Earth days at a distance of around 150 million kilometres, in other words, 1 astronomical unit. The masses of A2 Cruus and the larger component of A1 Cruus are expected to eventually explode as core collapse supernovae, ending up as neutron stars, while the smaller component of A1 Cruus could survive as a white dwarf. The left-hand and second brightest star in the Southern Cross is called Beta Cruus, and it's also a spectroscopic binary, consisting of two stars orbiting each other every 5 Earth years, at an average distance which varies between 5.4 and 12 astronomical units. Beta Cruus is located some 280 light-years away. The primary star, Beta Cruus A, is a spectral type B beta Cepheid variable blue star, which changes in brightness over a period of around 4 to 4.5 hours. It has about 16 times the Sun's mass, about 8 times its diameter, and a surface temperature of some 27,000 Kelvin. By comparison, our Sun has a surface temperature of just 6,000. The second star in the system, Beta Cruus B, has about 10 solar masses. A third companion has also been detected in the system. However, it appears to be a low-mass pre-main sequence star which hasn't yet commenced nuclear fusion. Near Beta Cruus is the spectacular young open star cluster known as the Kappa Crucis cluster, or NGC 4755, and more commonly referred to as the Jewel Box, the name given to it by famous 18th century astronomer John Herschel. Open star clusters are groups of stars which were originally all born at the same time out of the same collapsing molecular gas and dust cloud. Although somewhat still gravitationally bound to each other, stars in open clusters eventually separate, moving to other parts of the galaxy. As the name suggests, the Jewel Box is a stunning collection of more than 100 bright, colourful stars, located some 6,440 light-years away, although its exact distance is somewhat difficult to determine because of the nearby Coalsack Nebula, which obscures some of the light. The Coalsack is a dark nebula containing lots of gas and dust blocking out background stars. In Australian Aboriginal Dreamtime legend, the Coalsack forms the head of the Emu constellation, with the dark dust lanes of the Milky Way forming the emu's body and legs. The central parts of the Jewel Box are framed by bright stars making up an A-shaped asterism. These are among the brightest known blue, white and red supergiants in the Milky Way. Gamma Crucis, which is located at the top of the Southern Cross, is the third brightest star in the constellation. It's also one of the nearest red giants to our solar system, located just 88.6 light-years away. Although only 30% more massive than the Sun, its expanded outer envelope is bloated out to some 84 times the Sun's radius, and is radiating some 1,500 times more luminosity than the Sun. As a red giant, no longer on the main sequence, Gamma Crucis is nearing the end of its life. Its surface temperature is some 3,626 Kelvin, and it has a prominent reddish-orange appearance. The star on the right-hand side of the Southern Cross is Delta Crucis, a massive, hot and rapidly rotating star that's in the process of evolving into a red giant and will eventually end up as a white dwarf, the stellar corpse of Sun-like stars. Delta Crucis is located some 345 light-years away and has about 9 times the Sun's mass and 8 times its radius. It's presently radiating at around 10,000 times the luminosity of the Sun at an effective temperature of 22,570 Kelvin, causing it to glow with a blue-white hue. The smallest star in the Southern Cross is Epsilon Crucis, which is located in the space between Delta and Alpha Crucis. It's a red giant, some 228 light-years away. It has about 1.42 times the mass of the Sun and about 32 times its radius. Its surface temperature of 4,148 Kelvin means it's sometimes referred to as an orange giant. The Southern Cross is at its highest point in the southern sky this time of year and is pointing directly at the southern celestial pole. It's within the constellation Centaurus the Centaur, the half-man, half-horse of Greek mythology we mentioned earlier. The creature is holding a bow loaded with an arrow. The Centaur's front leg is marked by the two pointer stars Alpha and Beta Centaurus. His back arches over the Southern Cross, and just above this is Omega Centauri, a spectacular globular cluster visible with the unaided eye from dark locations. Unlike open star clusters, globular clusters are tightly packed spheres containing thousands to millions of stars, which were originally all thought to have been born at the same time from the same molecular gas and dust cloud. Omega Centauri is about 16,000 light-years away. It's one of the largest and brightest of the hundreds of globular clusters known to orbit around the Milky Way galaxy. Centaurus was included among the 48 constellations listed by the 2nd century astronomer Ptolemy, and it remains one of the 88 modern-day constellations. The constellation Orion the Hunter is still clearly visible in the northwestern sky this time of year, with its rectangle of 4 stars surrounded by a central trio of stars which form Orion's belt. To the right or east of Orion is the constellation Gemini and its 2 brighter stars, Pollux and Castor. This time of year, the Gemini twins are almost directly due north for Southern Hemisphere sky watchers. The higher of the 2 stars, Pollux, is a red giant, some 11 times the diameter of the Sun and located just 34 light-years away. The other star, Castor, is much further away, some 51 light-years. Look to the east and you'll see the star Regulus, the brightest star in the constellation of Leo the Lion. Regulus, which means Little King, is located 77 light-years away, and it's about 3.5 times as massive as the Sun and about 140 times as luminous. Regulus is a binary companion star, which takes 130,000 years to orbit the primary. To the right of Regulus, and virtually due east in the sky right now, is the star Spica. Located directly below the 4 stars in the constellation Corvus the Crow, Spica is the brightest star in the constellation Virgo. Also known as Alpha Virginis, it's the 16th brightest star in the night sky, and is another spectroscopic binary, comprising 2 stars closely orbiting each other every 4 Earth days. In fact, the 2 stars in Spica are orbiting so close together that the gravitational interaction between them has caused them to become rotating ellipsoidal variables, distorting them into the shape of a rugby league or gridiron football. Light from this binary changes in brightness as the 2 stars orbit each other, exposing their elongated hemispheres to us. Spica is located some 260 light-years away and is some 2,000 times as luminous as the Sun. Spica means ear of wheat, which Virgo is holding in a hand. It's so named because it marks the start of the harvest season in the Northern Hemisphere. The primary is the blue giant variable Betterseiad, which undergoes small rapid variations in brightness because of pulsations in the star's surface thought to be caused by the unusual properties of iron at temperatures of 200,000 degrees in the stellar interior. It has about 10 times the Sun's mass and about 7.5 times its diameter. Once a spectral type B blue-white main sequence star, it's now pulsating rapidly, rotating at more than 199 kilometers per second over a 0.1738 Earth-day period. It's one of the nearest stars to the Earth, which is expected to end its life as a Type II core collapse supernova. The second star in the system is also thought to be a spectral Type B blue-white giant, about 7 solar masses and 3.6 times the Sun's diameter. Okay, going back to the Southern Cross and looking to the right or west, you'll see the star Canopus. It's the second brightest star in the night sky after Sirius. Even though Canopus is 312 light-years away, it looks incredibly bright because it's huge, 100 times the diameter of the Sun and 10,000 times as luminous. This year's second major meteor shower, the Lyrids, will peak on April the 22nd and 23rd. The Lyrids appear to radiate out from the constellation Lyra, close to the star Vega, one of the brightest stars in the sky this time of year. The source of the meteor shower are particles of dust and debris shed by the long-period comet C1861 G1 Thatcher. Sky watchers in the Northern Hemisphere get the best view of the Lyrids. However, listeners at mid-Southern Hemisphere latitudes can also see the shower between midnight and dawn. Patient observers will be rewarded with around 18 meteors per hour before dawn from dark sky locations. And now, with a look at what else is happening in the April night skies, we're joined by Jonathan Nelly from Sky and Telescope magazine.
Hello, Stuart. Well, it's the middle of autumn here in the southern hemisphere, so we're starting to get to the winter constellations now. They're starting to make an appearance. So as night falls, we can see the Milky Way stretching across the sky from the southeast to the northwest during the first half of the night. By the early morning hours, with the Earth having turned a bit more on its axis, the Milky Way will now stretch from the southwest to the northeast. And how much you see of the Milky Way, by the way, will depend on how dark your local skies are, the area around where you live. And the darkness of your skies, I have to say, depends on how much or how little light pollution there is, which is street lights, sporting field lights, house lights, advertising and shop lighting and so on. It's a real problem for most people because most people live in cities and you've got all this wasted light. Most light that is out there from these artificial lights at night time, most of the light just goes anywhere except where it's meant to go. It's usually just meant to illuminate the ground, but it's going sideways and upwards and all over the place. It's just crazy because it not only ruins the night sky, but it's just a lot of wasted energy too. What's the point of lights shining sideways? It's just all lights. Street lights should have hoods over them that direct the light downwards rather than shining out the side and up into space. The very old style, sorry, I'm on a rant here, the very old style traditional long, thin, fluorescent street lights. I seem to recall data from years ago showing that 80% of the light coming out of those things didn't go on the ground. It just went in every other direction. Think of all the coal and stuff that's being burned to produce 80% of light going somewhere where it's not supposed to be. And that's why you can see these pictures of the Earth at night time. You see all the city lights and everything. What's the point of all that light shining upwards so that satellites can see it? It's just wrong. It's just totally wasted light, totally wasted energy. Anyway, that's my rant. That's what ruins seeing the Milky Way in the cities because there's so much light pollution around that the fainter stuff up in the sky, and the Milky Way is faint, it just gets drowned out. Anyway, as the night rolls on and the Earth keeps turning, a lot of the famous constellations that we've had around the last few months are going to start to drop out of view in the west, such as Taurus and Orion. Others, such as Gemini and Leo, can still be seen in the northern part of the sky, as seen from the mid-southern latitudes or in the southern part of the sky if we're in the northern hemisphere. Deep down south in the early evening, the Southern Cross is nice and high. It's up really nice and high. We've got the bright star Canopus, the second brightest star in the sky. It's up even higher in the south-southwest. And the brightest star in the sky, Sirius, is very, very high. In fact, from where I live, it's almost overhead this time of year in the sort of early to mid-evening. And it's because it's the brightest star in the sky. Of course, you just can't miss it. I mentioned Canopus. Canopus is the bright star in the constellation Carina. If you use a star map or one of those mobile phone apps that shows you what's up in the night sky to identify Carina, then grab yourself a pair of binoculars if you've got them and just start sweeping through the star fields of Carina, the star clusters, the nebulae and all this sort of thing. And even if you are in light polluted skies, you're still going to see quite a lot. Binoculars are what you need for this area. It's just really amazing and beautiful. Once you get the view of the night sky through binoculars or a small telescope, you think, wow, because the stuff you just can't see with the naked eye, it's too dim for your eyes to pick up at night time. But just with a little bit of optical aid, a bit of extra magnification and the extra light gathering power, having larger lenses than your eyes are, it pulls in more light and it's magnified and you start to see all this amazing stuff up there. So give that a try if you've got a pair of binoculars or you know someone who has. To the left of Carina, if you're looking south, we've got the Southern Cross, and right next door to it is a big dark nebula called the Coal Sack. And then very close to that are two stars known as the Pointers. I call them the two pointers, and they're Alpha and Beta Centauri. And it's interesting when you look at some of these stars because their brightness can't be used as a way to judge their distance from us, because a nearby dim star might seem brighter than a more luminous star that's much further away. So, for instance, you've got Sirius, the star that seems to be the brightest. It's only 8.6 light years away. But Canopus is 310 light years away, but it appears not that much dimmer than Sirius, really. That's because intrinsically Canopus is a bigger, hotter, brighter star than Sirius. It's just that it's 310 light years away and Sirius is 8.6. So Sirius is a smaller, dimmer star than Canopus, but it's so much closer, and that's why it appears brighter. So when you look up and you see stars, you think, oh, that star's really bright. It must be close to us. That's not necessarily the case. Some of the dimmer stars out there may be dozens of times brighter than the brightest star you can see. It's just they're a lot further away.
And this is all different from magnitude when astronomers are looking at the brightness of something in the sky.
Well, yeah, magnitude is a measure of brightness. So we say that star's a magnitude 1 star. A magnitude 2 star is dimmer than a magnitude 1. A magnitude 3 star is dimmer than a magnitude 2. A magnitude 0 star is brighter than a magnitude 1 star. and a magnitude -1 is brighter than a magnitude 0 star. Sirius, I think, is -1.5, 1.6, something like that. So it's the brightest in what they call apparent magnitude. Now, there are two different magnitude measurements. One is apparent magnitude. That's how bright something appears to us when we look at it just up there in the night sky, right? Not taking into account its distance from us. It's just how bright it appears to us. So Sirius appears to be very bright. It's the brightest star in terms of apparent magnitude up there in the night sky. Canopus is the second brightest because it's not quite as bright in apparent magnitude. But then the other magnitude scale is what they call absolute magnitude. This is where you even out the distances. So if you say if Canopus and Sirius were both at the same distance from us, which would be the brighter one? And so they've got these magnitude measurements for pretty much all the stars up there. So the absolute magnitude is a more, well, it's a measure of the intrinsic luminosity of a star. So if you had all the stars lined up at the same distance, then they all would appear to be certain brightnesses. But the fact is that stars aren't at the same distances from us. So when astronomers and people like myself talk about how bright something is in the night sky, we're talking about apparent magnitude, just how bright it appears to us at whatever distance that object happens to be. But as I sort of explained, you can't judge how bright something really is just based on what we're seeing up there, because a dim star might have a very low apparent magnitude, might be very dim in apparent magnitude, how we see it, but it could be intrinsically very, very bright and luminous in its absolute magnitude if we put it all at a standard distance. Does that make sense? So, there's just two scales. So when for observational astronomy, we're talking about apparent magnitude. When scientists are dealing with sort of astrophysics things, they tend to work on the absolute magnitude. If they're even using that at all, it's more reliable, equitable, evened out scale where all the stars would be at the same distance from us.
Well, that explains it. How about the planets? What's happening there?
The planets. Well, the planets up in April this year. Well, let's look at them now. As the evening sky darkens, you won't be able to miss seeing Jupiter, I can tell you. If you go out and look in the west, that's the direction that the sun sets. Once the sun's gone down sufficiently and the sky's dark enough, and it doesn't need to get too dark because Jupiter is bright, you will see Jupiter. It looks like a big, bright, prominent star above the northwestern horizon. Now, if you have a pair of medium-sized binoculars or a small telescope, or you can get hold of one, take a look, and take a look at Jupiter, and you should be able to see up to 4 tiny dots near the planet, tiny bright dots, perhaps 2 on one side and 2 on the other side, or 3 on one side and 1 on the other side. These are Jupiter's 4 largest moons, the ones that Galileo spotted through his first telescope. That's how they get their name, the Galilean Moons or the Galilean satellites. And they are bright enough that you can see them through a pair of binoculars. Some people who have really good eyesight, and some kids have actually reported this, you have super eyesight, have actually been able to see these tiny pinpoints of light just with the naked eye, in the good seeing conditions where there's not too much turbulence in the atmosphere and the tiny light from these little moons can get through.
And they see the Galilean moons? That's amazing.
Yeah. People with super eyesight have reported seeing them. No chance I'd ever see them with my eyesight, even with glasses on. But the great thing about them is that these moons zip around Jupiter so quickly that if you go out and look at them, say, after the skies got dark, and you won't be able to do this at the moment because Jupiter's going to set a couple of hours after sunset. But if you've got a time of the year when Jupiter is up all night, then you can go out when the sky gets dark, have a look, see what the positions of the moons are, and then if you check, hours and hours later during that same night, perhaps go to bed and get up early in the morning when it's still dark and have another look, you'll see they've all moved because they're orbiting around the planet. And sometimes they move in front of each other, sometimes they disappear around behind Jupiter, sometimes they just disappear into Jupiter's shadow. Very slow, real-time entertainment, if you like, astronomical entertainment. But it is really amazing to see. And it's one of the things, of course, that Galileo saw and figured out, hey, what we thought before telescopes was the unchanging heavens, when everything's static, everything's the same, everything's perfect, everything's pure. And then all of a sudden looks through a telescope and thinks, there's things whizzing around other things out there, a bit like the moon whizzes around the Earth. So
that was the revelation point for Galileo, wasn't it? That was the...
Yes, and pretty much, we're not that special because it's happening out there too. And if it's happening with Jupiter, it's probably happening with the other ones, and so on and so on and so on. So, a lot of people credit this sort of thing as being part of the start of the scientific revolution, basing stuff on observation and evidence rather than just dogma and mythology and that sort of thing. Anyhow, got off track a little bit. We're talking about the planets. All the other planetary activity at the moment is happening in the morning sky, so you've got to be up early or getting home late after night shift. First up, we've got Mars, which is rising at about 4:30 a.m. Sun at the start of April. Close behind it, very close behind it, is Saturn, rising only about half an hour later. And then an hour after that, Venus will rise too, all pretty much in the same part of the sky. Now, it's easy to tell these three planets apart because Mars has a reddish-orange colour. Saturn is about the same brightness as Mars at the moment, but it's a white colour, possibly with a slightly yellowish tinge. I often think it's got a slightly yellowish tinge. And Venus is very different to both of them. Venus is far brighter and it's bright white, so you're not going to miss it. So Mars comes up first, then Saturn, and then Venus. And if you take a look in the morning, go out the morning of April the 11th, you have to get up nice and early, you'll see that Mars and Saturn will have sidled up to each other. Because they're moving in the sky as each night goes past. They're moving a little bit. And at this particular time, they're sort of moving towards each other as seen from Earth. And on the morning of the 11th, they're only about half a degree apart, which is really quite close. Of course, they're a long distance apart in real terms out there in space. But just from our point of view, our line of sight, they're only half a degree apart. And that is going to look really, really spectacular. So fingers crossed for some good weather on the morning of April the 11th. Set your alarm clock, get up early and have a look at that. It should be really good. And that, Stuart, is the night sky for April.
That's Jonathan Nelly from Sky and Telescope magazine. And this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.